Hey folks, we're going to wrap it all up with this second law of thermodynamics. There's some really exciting stuff that's going to happen. I'm excited by it. Maybe you're like, what the hell has Harmon been talking about for the last hour? It's going to get exciting because we're going to put all of this stuff together. And what we're going to start seeing, and this will probably be more into the next section on chapter 4, we're going to see how physical observables, things like melting, boiling, other like extremely fundamental properties of the universe, how they all come together from these equations, from the Maxwell relations, the first law of thermodynamics, the second law of thermodynamics. It's all going to come together. And when we have something as powerful as the fundamental equation, we know that this is important stuff. So what is the fundamental equation? Well, first I'm going to start by writing the first law. du equals dq plus dw. Okay. That's our first law. Okay. We also know from the second law, and there's a number of ways we can write the second law, but one of those is dq reversible equals TdS. Okay. Second law. Okay. I'm also going to write that dw reversible, we're just collecting all these equations that might help us out, is negative PdV. And now I'm going to combine all of these equations into one master equation called the fundamental equation. And you know, when we're combining the first law and the second law into a master equation, this is super important. Okay? So how does this go? So this says now du equals, okay, well, I'm going to say we're going to make this a closed system for one. So that gives us the canonical. Canonical. All right. Wow, I can't write it all. Canonical, right? The canonical system is our closed system that can exchange heat but not number of moles. Okay. And so now I can rewrite this dq reversible right up here as TdS. Okay. And I can rewrite, you know, if I'm saying this is all reversible, that's what makes it closed. Okay. Then I can say negative PdV. There it is. du equals TdS minus PdV. That's a super important equation, and you're about to see why. Okay? So if we have du equals TdS minus PdV, all right? U is a function of S and V. And we note that U is a state function. And we remember from what seems like a lifetime ago, it has an exact differential expression. Okay? That means I can write the total differential of du as the following. And I'm going to ignore all this other crap that I've written on the slide, and we're just going to note, okay, we see u is a function of S and V. We impose it as an exact differential, which will go as follows. Partial of u with respect to S at constant V ds. Now the other relationship, partial of u by the partial of V at constant S dV. Okay? And now this is powerful because we have here this fundamental equation. Let me write that right underneath. du is T ds negative minus P dV. Why is this so powerful? Why am I excited about it? Why am I making such a big deal? Because this is going to give us the thermodynamic definitions of temperature and pressure themselves. Check this out. The partial of U by the partial of S at constant V equals temperature. And in fact, saying, looking at how U changes with entropy at constant volume, so the partial of U with respect to the partial of S at constant V is a better indicator of temperature than temperature itself. In fact, it is temperature. So we've talked about how temperature is really just, it's a human construct. It's a thing that I can measure, okay? How hot is it outside today? What's the temperature, okay? What that really means, the bigger picture for the universe, is this. That's really what temperature is. Super cool, okay? Well, what about pressure? And we know that there's a negative sign in there, and that's okay, okay? But the partial of U with respect to volume at constant entropy, negative, is pressure. And we remembered, hopefully we remembered, back from our Joule-Thomson discussion, that the units of U divided by V give us pressure, okay? So that's really, really cool, okay? And so what else is going on? So what else can I say from this, all right? Well, we remember that because du has an exact differential expression, okay, I can say the following. So I'll remind you of the math. dF equals g dx plus h dy. And this is a reminder of all those exact derivatives we did. So now if I take the partial of g with respect to y at constant x, that's going to equal the partial of h with respect to x at constant y. And I didn't put this in before, but we also recognize, because this is already a differential, these two are actually going to give us the second derivative of f with respect to x and y. Okay? So why is all of that a big deal? Well, now let's play with this fundamental equation, okay? And let's do exactly what I just did. So now, partial of t with respect to v. So remember, just like I did here, I said g with respect to y. So now let's do t with respect to v at constant s, okay? Equals. So now we've got h with respect to x at constant y. So that's going to go equals, and then I've got a negative sign there. Negative partial of p, okay, with respect to s. I'm putting this together in the exact same way here. And now that's all at constant v. And now following the same way I put this together, all of that's going to equal the second derivative of u with respect to s with respect to v. But bam, if I had a mic, I would drop it. If back in the day when we were in the classroom, I used to do the LeBron James. I take the chalk, throw the chalk everywhere. I'm the LeBron James of the chalkboard. Why am I so excited? This is a freaking Maxwell relation. Holy shit, right? Do I have an extra piece of paper? Let's keep going here. Let me put an extra piece of paper here, okay? Right? V, A, T, U, G, S, H, P. Arrow this way. Arrow this way. So we were just playing with U. Okay. U is sandwiched between S and V, which equals derivatives at constant S and derivatives at constant V. The derivative at constant S goes partial of t, right? Travel the arrow. Partial of t by the partial of v at constant S. The derivative in v, now I'm going against the arrow, so negative sign. Partial of p by partial of s at constant v. That's the same thing we just came up with. This is awesome. If you don't think it's awesome, that's okay. You don't have to do physical chemistry in your life. But I think it's awesome. I think this is totally cool. This is where these relationships come from, okay? So let's keep going with this, okay? And so there's a bunch of proofs we can do. Like I didn't do this before. Let's see what I have coming up next. Yeah, okay. So we talked about this whole internal energy thing, or excuse me, internal pressure. So we talked about this earlier, that the partial of U with respect to V at constant T is this internal pressure, which we said is 0 for an ideal gas, and we said is A times N over V all squared for a van der Waals gas. Where does that come from? Well, it actually comes from the Maxwell relations. I'm not going to finish through this, okay? But if we were to go through, starting with partial of U equals, right, the partial of U by the partial of S at constant V ds plus the partial of U by the partial of V at constant S dV. If we were to start here, okay, it can be shown. I'm just going to like kind of show you, hint, hint, wink, wink, how you start this derivation. Pi t from the Maxwell relations, you can put this all together. That this all equals a partial of P by the partial of T at constant V minus P. And then from there, this leads you to A times N over V squared. So we can use these Maxwell relations to come up with other relationships that we maybe didn't know existed before. So they really are a cipher or a code for the universe. That's how I really like to think of these Maxwell relations. They give us the key to physical observables of the universe. I'm going to show you some even bigger ones here. I'm going to skip. I think I gave myself too many slides. So I'm going to show you another really big one here with Gibbs. Okay? And I'm not going to derive this full equation, but it can be shown. The fundamental equation for Gibbs. So if we start with du equals TdS minus PdV, so that's our fundamental equation, right? Then let's see here. I'm trying to show you enough that, yeah, so, okay, I'm sorry. I'm looking at the time here, and I've got time to derive this. Apologies. Let's go through it, okay? Let's start with G. By definition is H minus TS. Or, in other words, dG equals dH minus dTS. So we're going to take the derivatives of both, okay? So dH minus TdS. And the reason why we didn't take derivatives of both last time is because we played the game where we say hold this constant, now hold this constant. Okay, now I'm going to play a game where I'm not holding either of them constant, and thus I've got to do the chain rule. So dTs first gives me TdS minus S dt. So that would be my chain rule. Okay. We also know that by definition H, so 3 lines there means that's a hard definition, is PdV. And we'll also keep going here where we're not concerning ourselves with what we're holding constant yet. I'm going to do this generally, okay? Equals du plus P dV plus V dP. So we're full treatment here, okay? So now I can say that dG equals, all right, I know dH is all this, so let's write all that down, okay? So dH is all this junk. So that's du plus PdV plus V dP, okay? And that's now minus TdS minus SDT. All right? So now, applying the fundamental equation, okay? So the fundamental equation says du equals TdS minus PdV. And let's see, I've got a TdS right there, and I've got a PdV right there. All right? So now, let's see here. I lost track of where I am. Okay, so now I'm going to say dg equals. So, oh, I know what I'm going to do. I'm going to plug in du right there. That's what I'm going to do. Okay. It's Friday afternoon. You can tell by my thing that it's 4:59 p.m. Getting tired, getting ready to go have a beer. Okay. So dg equals all of this, TdS minus PdV. So that takes care of just the du. Now, plus PdV plus VdP minus TdS minus SDT. Okay. And you can see those two terms cancel, as well as the TdS. That cancels as well. And what I'm left with is another version of the fundamental equation, dg equals VdP minus S dt. Okay? Now, we can play the same game we did before. We recognize that g is an exact expression that's a function of p and t. Cool. Great. And because we know g is a state function, I'm going to say dg, because I can see that it's connected with p and t, right, is the partial of g with respect to p at constant t dp plus the partial of g with respect to t at constant p dt. And once again, doing this game reveals something awesome and powerful and unexpected. So I'm going to write both of these equations next to each other. And this reveals more the connection of physical observables to thermodynamic potentials. So for example, you can see here from this that by definition, volume, something as fundamental as volume, is actually the derivative of Gibbs with respect to pressure at constant temperature. That's really cool. That is actually what volume is in a broader sense, right? In a bigger picture sense, okay? Or what we can also see connecting these two, right? So this is how I connect these, okay? Just from inspecting these equations, right? So now we can see that this derivative, partial of g by partial of t at constant p, is by definition entropy. Really, really cool stuff. And if we were to go to put this together, I'm going to cut it off now because I think you can kind of see where this is going, but I could use this exact same thing. I could do the thermo square from this, right? I could say from here, connecting all of those relationships, okay? Let's just do it. Let's do it real quick. I'm sorry, I'm so indecisive today. So how did I do that, okay? Okay, so here's how we do that. So we know that dg equals partial of g by the partial of p at constant t dp. My handwriting is also starting to fail horribly. Partial of g by partial of t at constant p dt. Okay, so the way this works is, and I also recognized that this derivative was equal to v, and this derivative was equal to negative s. Okay? So if now I start with that derivative, v. If I say now the partial of v, which I recognize was being held at constant t, so I really want to look at the other variable, right? So that's going to be partial of p at constant t equals, so we got a negative sign, negative. And then now I'm talking about this relationship, s. And now I'm going to compare it to this side, which is constant p, right? So now I look at t, so I switch the two bottoms, right? Okay? And all of that, wait, did I get that backwards? I got that backwards. Okay, let's talk about why I got that backwards. Oh yes, okay, so I'm going to start with v. I recognize from my fundamental equation, dg equals v dp minus s dt. Okay? So I'm going to start with v. I'm going to say partial of v. And aha, yes. So v here is tending on p. I got to switch that. Now I got to switch v to t. Okay. At constant p. And then now there's the negative sign. Now I've got s. And now s is, with respect to t. Let's switch it over to p this time. Now s with respect to p at constant t. And we recognize that that is the second derivative of g with respect to t and p. Let's see if I did it right. Let me start a new thermo square. VAT UG SHP, arrow goes this way, arrow goes this way. Here's G, little horseshoe. So we can see G is sandwiched between T and P. Okay? And we know that that's going to mean derivatives at constant T and derivatives at constant P. So if I travel up the P arrow, I get partial of V by the partial of T. And then now if I travel down the T arrow, right, I'm going down the arrow, so that's a negative sign, and I end up at S. Partial of S by partial of P. And yes, that all worked out. Beautiful. Okay. So we're going to move into talking about phase equilibria. These relationships, these derivatives, are going to tell us about phases. We're going to learn even more about the universe from these relationships. Okay? So these are powerful. This is powerful stuff we're talking about. Like the thermodynamic definition of volume, temperature, pressure. We take these for granted, right? We call these a state. They are, in fact, a state, right? And we see the bigger picture of what's really going on. In this case, all of this is related to the canonical description, okay? Those states come from the mathematical relationships of our thermodynamic potentials: energy, enthalpy, free energy, Gibbs and Helmholtz, okay? Awesome. I'm sure you're going to have loads of questions because this is definitely where thermo goes into crazy world. So please, I know I didn't describe any of this perfectly, so please let's have a discussion if need be. Ask me all the questions you want. Okay, folks. Hasta mañana. I'm not going to see you tomorrow. I will see you later. Okay.